So I guess we're going to start. Again, greetings to all. My name is João Dias. I'm from MAC, and I'm here to introduce you again this initiative that's a joint webinar series between BigHPC project and UT Austin Portugal Program. I should thank you all for coming. And this webinar will have with us Bruno Antunes from Wavecom to talk about monitoring in the big data era. So, Bruno Antunes is a research manager and product developer from WaveCs at Wavecom. He obtained the Electric and Computing Engineer degree, a 5-year bachelor from the University of Coimbra. He concluded the curricular component of the Computer Networks and Communication Service, Masters from the University of Minho, with the outcome of his master's split thesis, modular platform for wireless communications based on open source software, leading to the launch of WaveC's multi-radio platform. He's currently attending the PhD in MapTele doctoral program in telecommunications. Prior to the current functions, he also worked as an external consultant at Wavecom for development and launch of WaveC's multi-radio platform, and after that, with a mobility scholarship from Wavecom at Innova RIA. Since January of 2016, he assumed the tasks of R&D and R&D management at Wavecom in several funded projects, such as WaveCs, Hyper Wireless, Marcom, Mobilizer 5G, 5G Perfecta, and BigHPC, while continuing to support implementation and installation of the WaveC's radio. The moderator will be me. I'm João Dias. I have a master's in computer science with a specialization in bioinformatics and high-performance computing, and I'm currently acting as a sysadmin at Mac. So I urge you to interact with us. You may use the Q&A for that. Throughout the presentation, there will be no discussion. However, in the end, we'll have some moments for you to make all of your questions. For more technical issues, you may use the chat at Zoom. So to maintain yourself muted at all times. In the end, if you did not make any questions in the Q&A, you may just raise your hand and I'll give you the word and you can have your say. So that's all for me. I'll share now. I'll give the presentation now to Bruno. So the screen is yours, Bruno.
Hello, good afternoon. Good afternoon to you all. Let me just share my screen. I think you can see my slides, right?
Yes.
Okay. Good afternoon to you all. And as João said, welcome to the third webinar of the BigHPC project. This one, the third one, is dedicated to the subject of monitoring in the BigHPC era. So a brief outline of what we're trying to address in the next half an hour or so. We will first talk about a little introduction about HPC centers and the containers utilization on them. Then an overview of the increase of usage in HPC center by big data applications and their specific challenge. Then I will carry on with presenting the BigHPC project and its proposal to monitor this infrastructure with this big data scenario in mind. And last, I'm going to share with you the current results and the next steps for the monitoring component. So for those of you that have already attended the previous webinar and already know what is an HPC, and I'm sure that most of the audience already know what's the HPC, we can consider it as a lot of connected computers or nodes. These nodes are meant to be accessed by researchers, tens to thousands of researchers concurrently. And they are mostly used to solve complex mathematical problems in areas so diverse such as finance, physics, weather, astronomy. Pretty much every area that needs high intensity computing benefits from using an high performance computer. Nowadays, these infrastructures are also being used to solve big data and machine learning workloads. Recently, container technologies are being applied in HPC infrastructure. This is allowing developers to bring their desired applications onto the HPC world. The benefits of using containerization, it's that eases the development of the computer workloads with a concept of developing like at home or like at its own PC. The advent of containers is coming in parallel with an increased demand of what we call user-defined software stacks that require custom libraries, custom build environments, and in some cases also completely entire operating systems. Also, using containers enable us to make the best use of the heterogeneous infrastructure that are typically available on an HPC center. Work previously done at TAC has proven that the overhead of containers in regarding to bare metal deployments is very low. Also, from our second webinar, is HPC ready for big data storage? Reminding that big data workloads, the workloads that we are going to focus here on this project, are what we call data-centric. This means that they have intensive I/O with lots of random, frequent, and small read and writes to the file system. And also the software in use is highly specialized and it's always evolving. So there are always newer versions. And this also, it's interesting to explore the use of containers on these scenarios. These applications are what we call data-centric. And most of the times the software that is in use was not developed with time sharing environments in mind. This tends to lead to irregular workloads that with requests for unpredictable resources and also the need of persistent services. For this specific project, the BigHPC, we are tackling what we call the storage bottleneck, the scenario where the number of compute nodes are stressing the storage component or the parallel file system. Regarding monitoring, the usual challenge of monitoring is some of the challenges, I'm going to talk to you about some of the challenge are going to be amplified by this kind of infrastructure, by HPC infrastructure. The number of variables for each node to monitor is big, and there are hundreds and thousands of servers that are composed by multiple nodes. This tends to generate a lot of data that must be stored. Some must be stored for historical purpose, like the cluster usage, workload status, accounting purposes, and other that may be discarded after some time, maybe after the workload is finished. In that sense, we must choose carefully which metrics to collect, to store, and what we don't need to collect. We have to pay special attention because we may fail to collect precious information that may well be needed in the future. Other challenge that we can identify are the sampling interval. Too low and we may not capture the necessary metrics. Too high and it will generate excessive information that will prove difficult to manage. Lastly, a very important one is don't impact the cluster or have the less impact in the cluster as possible. Desired value for a monitoring component would be less than 5%. So the monitor agent shouldn't consume necessary resources for the compute workloads. There are already, of course, a lot of solutions or tools to monitoring HPC infrastructures. What we have found out is that some or most of them aren't still focused on this big data use case, where we need to take special care of the storage I/O. Others, the main cons that we found were that they are of complex implementation and very difficult to replicate, or were specifically developed developed to one HPC center. So the metrics are only available on those clusters. But we don't want to reinvent the wheel. We don't want to have another protocol, another architecture, another framework. So the big HPC project intends to solve this challenge, resourcing to three main components. A virtual manager that will be responsible to store, curate, and manage the container files. These container files will optimally be deployed in the different hardware that is available at the HPC centers, and will also be responsible to launch these containers, these images. Also, another component is the store manager that will be responsible to keep track of the I/O health and keep track of what is the status of the file system. And last, what we'll be focusing more during this presentation, and what we are focusing more during this presentation, is the monitor backend that will inform both the storage and virtual manager of the cluster and the workload status, while also be responsible for storing data from the workloads to later analysis. Specific challenge to this scenario: we don't have root access to the nodes, so by using containers and unprivileged containers with singularity, we can only measure public exposed values or our own user monitoring. So we are going to, our proposal is to run the monitoring component alongside the container, and this means that we are limited by the number of metrics that we can collect. We won't be able to collect other user metrics, for example. Also, another challenge specific to this project, we wanted to be able to share the same database, and we have different requirements regarding to the database. We want to have a long scale metrics or long-term metrics, and this will be given access to the database. And also we want to have real-time metrics or short-range metrics that we must give access to an endpoint. The monitoring backend is responsible to inform the virtual manager of the status of the running workloads, and the cluster, as a whole, needs updated info for where to allocate a workload. Additionally, it must provide the storage manager with the most up-to-date information about the storage user, because failures in the HPC affect the current running jobs and waste scheduling and queuing time. Regarding our recipients or the targets of the work we are going to develop, we can classify them in two groups: the sysadmin that want to know how the cluster is performing, so they want to receive, when necessary, alerts of malfunctioning or nodes that are misbehaved or misbehaved workloads. They also need long-term monitoring for accounting purposes to better understand what has been run on the cluster. They also need long-term. They also need, in the scope of this project, know when to launch the workload. So they must know when they can launch the workload, and for that they need real-time or the most up-to-date data. On the other hand, there are the users, the researchers that use the cluster for their workload. They are mainly interested in running their workload, but they are also interested in improving it. So they may want to detect execution points where the performance is low or can be improved, and they are also interested in visualizing their data or their simulation results. With that in mind, our proposal, we are trying to base ourselves in commercial off-the-shelf software. The main reasons are that it's easily available, it's well maintained, has a large user base and community support, and we think that most, or at least most users are or will easily be familiar with. For that, our proposal is based on a data aggregator, Prometheus, that is going to serve as proxy and caching of the real-time data in combination with the PromScale and the Prometheus gateway. Also, the database that we consider on using here is a timescale database, because timescale is an extension to Postgre and also benefits from the reliability, the tooling, and all the ecosystem around PostgreSQL. And also in terms of visualization, our proposal is the Grafana, since it's not close to any backend store or any vendor database. The monitoring probe that is responsible for gathering metrics is triggered alongside the workload container and will be pushing metrics to the system. Since we want this to be available and be easy to install on other HPC centers, we are targeting and developing everything on container technology. So an HPC center that has some kind of container engine will be able to run this architecture. Some detail about our monitoring probe, where the main of the work is being done. So what better to monitoring a container than another container? And here comes Hector. It's high performance container monitoring. It will be launched as a container parallel to the workload container. Currently, the collected metrics are the running processes and the system utilization. Information about the Lustre file system, but viewed from the user perspective, and also GPU and the InfiniBand, the interface responsible for transferring data from the file system to the compute nodes. In terms of dependencies, the dependencies are low, also because we only depend on the PSUtil library for the process and system utilization computation. And for the GPU, we must resource to an NVIDIA proprietary tool. The Lustre file system and the InfiniBand metrics are computed by scraping the system, the file system, the local file system for counters and information. This we consider that it also contributes to the intention of being easily implemented in other systems. The container will periodically expose the collected metrics to an endpoint and also to the push gateway, and I'll be explaining in more detail the function in the next slide. Hector. So Hector, our probe, is a container and exposes metrics to an endpoint that will be read by Prometheus. Since this endpoint only exists while the container is running, the push gateway function is to collect the last container metrics. So Prometheus is continually scraping the endpoint and the push gateway for metrics. And the real-time metrics can be pulled from Prometheus from the interface API. So any information that one wants to know about launching, for example, an workload will be available on the Prometheus interface API. Regarding the part of the storage, the metric storage of our architecture, since Prometheus was not designed in the ground up for analytics, PromScale scales and augments Prometheus for enabling for long-term storage and also analytics. Some of the selling points is that PromScale is built on top of ScaleDB, so it can be scaled horizontally. It supports native compression, downsampling, interpolation, and it's also natively supported by Grafana via the Prometheus and PostgreSQL timescale data sources. Prometheus writes data to PromScale connector using the remote API storing the data in the timescale database. Last, in terms of architecture, our our area of data visualization. The database can be queried with specific PromQL query language that is made for Prometheus, or any other type of SQL type queries. For example, if you want to generate simple graphs, just to visualize a workload, you can use PromLens. If you want to do more complex queries and more complex visualization scheme, you can use a more powerful tool like Grafana. Additional, any SQL query can be used to query the database. So a PromScale connector understands PromQL. It understands that its queries natively and fetch data from the timescale to execute them, while the SQL queries will go directly to the timescale database. So seeing our architecture as an whole, we consider that the advantage of the proposed architecture is that each one of the components can be replaced or can be easily adapted to any other alternative types. For example, the visualization tools can be adapted to fit the user needs. If a specific user is more has more experience with some component, you can choose its own visualization tool. Also, another key point, it's that since the architecture is based on container technology, all the components can be deployed on different hardware, thus coping with different HPC heterogeneity. And the only request is that there is already some kind of container engine. And until now, and during the course of the project, we have only validated Docker and Singularity, but we don't have any reason to doubt that it may be supported by other container technologies. This is an example, a simple example of data that we can showcase here, that we are already collecting. In this case, we can see two different types of metrics: counters on the right side of the vertical scale, and rates on the left scale. So this use case is where we transfer a remote file from a server. It is similar to fetch data from the parallel file system to the local storage drive of the computing node. We can see at minute 44 the increase of the transfer rate in the network and the corresponding increase in the network counter. Afterwards, we can see the disk counter increasing and also the disk write rate. And lastly, we can see that when the disk counter reaches approximately the 1 gigabyte mark, the size of the file, the transfer ends. This is just a quick example to show that the benefits of visualizing this kind of information, it's much interesting with a graph than with numbers. Concluding, currently the monitoring probe actor is capable of monitoring multiple nodes simultaneously. This is an impulse of course, an impulse of this system, because the workloads will typically be spread around 100 to thousands of nodes. We are configuring we are able to configure the pooling rate from 5 seconds to 5 minutes. This is limited by the scraping rate of Prometheus. The Prometheus scraping rate must always be the double of the container pooling rate for obvious reasons. Also, the container can be run with what we call time to live, so we can specify a time to live, and the container will end after that time. From our current tests, the CPU usage is around 1% of the CPU. So we are currently observing that this is only test data, 0.3 to 1 second of time to running the probe. And the process collecting metrics are the bigger ones, and are accounting of 95% the collecting time. After collecting a batch of metrics, the monitoring container sleeps for the duration of the pooling rate that we defined, and during the sleep mode, the sleep mode or the inactive mode, the impact on the CPU is neglectable, so it's not even accountable for. Next steps, what we are trying to do in the future, aiming at a pooling rate capable of being automatically adaptable to the type of workload running on the compute node. So we want that short-term high-intensity jobs, they require an higher pooling rate than medium to long-term small-intensity jobs. Additionally, we are also studying compression technologies to efficiently store the long-term data. One other area that we're working is the integration with the remaining of the component, the remaining component of the project, and also the scaling of all architecture. As it also is clear for all, this is a scenario where scaling this kind of components is very important. So I will end here. Don't miss our next webinar. We'll be addressing the visualization of data. Since humans are good, have a good visual capacity. I don't know if any of you find an interesting pattern on the example graph and the slides, but there was some event that triggered our attention in that slide. The BigHPC is a UT Austin 2019 strategic research project. It started on the 31st of March with a duration of 36 months. The consortium is composed by Wavecom, INESC, Tech, LEAP, UT Austin, TAC, and MAC. Thank you all for your time and patience, and I look forward to answering any of your questions.
Well, we don't have any questions so far. You guys are being shy, so I hope that you do some. Well, I'll start myself with one. Bruno, you say that you do long-term metrics. How do you say those? How do you plan to deal with those long-term short storage of metrics? I don't know if I'm.
So we identify here. We divided in terms of storage, we divided the metrics in those two big groups. What we call short-term metrics, we consider the metrics that are necessary for the virtual manager to run another workload. For example, he has to know at the moment he wants to run the workload, if there are available nodes and where and what are the available nodes to launch the workload. This is what we mean by real-time or short-term storage metrics. When we consider long-term metrics, we are looking at, for example, the workload utilization. Imagine a specific researcher has run its workload and wants afterwards to do some sort of analysis of the way the workload has run. And so he would like to understand and have access to all the data that was gathered during its workload. That's what we call long-term metrics. Additionally, in the concept of long-term metrics, there is a need to keep at least with a big interval metrics responsible for accounting, because you imagine that you want to do some audit, posterior audit to the system. You want to know what workloads have run and what have they done in order to, if needed, to account for misuse, for example, of a specific node. I don't know if that was the question, if I answered it correctly.
It was that. Another one. Is there any difference in the monetization requirements between scientific applications and the regular big data applications?
So the scientific applications, they have typically they are what we call well-behaved. So their behavior is predictable, and this kind of infrastructures are already well adapted to running those specific applications. One we're calling this scientific application, we're calling about simulation and those kind of application that I mentioned regarding astronomy, simulations of fluids. One hot topic of the moment was computing for COVID-19, for example. These scientific applications have an well-behaved and well-known behavior. The big data applications, what has been found is that they are I/O intensive, so they stress a lot on the file system, and the file system in these HPC centers is shared in parallel with other compute nodes and with other users. And so what has been found out is that these big data applications tend to stress a lot on the file system, and also they weren't really developed to be run on HPC. They were mostly developed to be run on single user nodes. Either the size of it doesn't matter, but they are usually not kind on sharing resources with other users. They are not built for time shared application, for time shared systems.
Okay. Well, we have a question from Julio Silva. I don't know if Julie wants to. I'm gonna give permissions to Julie to speak. So Julie, you can make your question. You can unmute yourself. Exactly.
Hello everyone. Can you hear me?
Not really well.
What about?
Okay.
You can hear me better now.
Yeah.
Oh,
it's
okay,
better now.
So I have two questions for Bruno. Namely, since you said that you do not have root access to the compute nodes, how do you plan to extract meaningful metrics from workloads containers, such as the I/O metrics?
Okay, thank you, Julie, for the question. That is one of the I don't want to call it disadvantage of using containers, but since we are not going to have a root access to the nodes, as I said, and you also referred it in the question, we don't have root access to the node, so we are limited in the number of metrics that we can capture. So one of the options that we are studying is launching the container alongside the workload container. So this would impact the impact on this is that we would need to change the job script that launches the container to work alongside the compute workload. So the monitoring container will have to run alongside the workload container. This is one of the options that we are choosing, that we are seeing. Another option is running all workloads and all the monitoring containers under the same group, the same BigHPC group. Since then, we will have the same permissions, and we could see other users of the same group. We can see their metrics. So this is an option. All share the same user, the same BigHPC user, and running all the workloads under this user. One third option that we think it's more far-fetched, that it's more out of our reach, would be to launch the monitoring container with higher privileges. This is a solution that may work well in the scope of this project, but probably if we wanted to try to use other HPC computers, it will probably be more complex to impose these higher privileges to the monitoring container. I don't know if I was clear.
You answered my question. Thank you. I just have one final one, if we have the time. So you guys talked about long-term storage of metrics. how do you plan to deal with that? How do you plan to deal with the metric? So you will have the database. The space is limited. So after a time, how do you plan to deal with the accumulation of metrics in the database?
Yes, that's a very interesting question, and this question is very important in this scenario, because since the number of nodes it's very high, and we'll typically be monitoring a lot of workloads. The data is surely to increase rapidly, and so this is going to be a problem. We are still in the very early stage of this. We are still currently exploring. One technique that we are finding out that may be interesting to use is downsampling techniques. So downsampling data as the data becomes old. This allows to freeing up the database, freeing space in the database without losing a lot of information of the stored data. We don't want to lose meaningful information, but we are still in a very early stage of this, and we are not clear. But we know that this is a real problem. Data is going to grow very fast here in this scenario.
Thank you, Bruno. Those were all my questions.
Okay, thank you, Julie.
Thank you, Julie. Does the audience have any other question?
I noticed that you commented. I don't know if the other users also had the same problem that when I was sharing the slides. I understand that there were some problems of me while sharing slides. Some of the slides were.
Yes, I saw some slides were broken. I didn't know if it was only on my side.
Okay.
But okay. I don't know if the audience wants to have any other issue or question to report. Okay, I guess not. So yeah.
Regarding okay.
Go ahead, Bruno.
Regarding the visualization slide, I set a little teaser on the end of the presentation to see if someone spotted an interesting behavior on that slide. I don't know if you noticed the strange or the.
I did not notice.
Okay,
so,
I can just.
So I don't know if you want to share it again, that slide, or you're muted.
No, it doesn't need to share the slide. I was just asking if someone in the audience spotted it. Yes, there was a little interruption on the rate when we were downloading the file, and I was just see that if anyone spotted the catch that interference on the transfer. But that's all. Thank you, Jean.
Okay, so I thank all participants for being here. I thank Julio for his questions. I guess it's time to close this webinar, and I urge you to stay tuned for the next one that will be about software-defined scientific visualization, and it will be with my colleague João Barbosa at January 20, 2022. And I guess that's all from my part. Thank you all again, and stay safe, and I hope to see you in the next webinar. So that's it.
Okay, bye-bye. Have a nice afternoon.
Bye-bye.